So for today, what I wanted to have, so we have covered all the content that I wanted to cover on special relativity. Now, the next step is to look at general relativity. But before doing that, I wanted to cover today something that is not related to relativity, but actually is quite important, which is quantum information, quantum computing. So how many of you are familiar with quantum computing? How many of you have heard about it? You can raise your hand in your, all right. So a couple of you, but not everybody, right? Okay, good. So maybe this is, a lot of it is new to you guys. So ask questions in the middle, okay? And then I'm giving you a presentation, so I won't be able to, I'm gonna make it full screen and I'm not gonna be able to see the chat. So if you have something in the chat, speak up and then I'll zoom into the chat, okay? So let me start the presentation. And where are you? All right, here we go. Can you see my presentation at this point?
Yes.
All right, thanks. So this is quantum information is one of the things that I do in my research group with a couple of a couple of undergrads have done research on this and grad students. So this is a cartoon that I used to have before we changed the logo, OSU logo. So a couple of years ago, I had this as the front page of my website, but now it's Optimus Prime. So if you guys go to my website, you won't see this anymore. And I don't know if I'll get to tell you about the research, but the research, some of it is in these two papers that I'm gonna show you. And that research was done. So there we go. Here, no, here, here, here. All right. So that research, can you guys see my mouse when I move it? Or is it not showing up?
We can see it.
All right. So this research was done in collaboration with Thomas Blasi. He got his doctorate, but when he was doing this, he was finishing up his diploma, which is the equivalent of a BS in Germany. And then with Professor Rick Heller, who was my boss at the time, a collaborator, Esa Rasanen from Finland, and Professor Bob Westerveld, who is doing experiments on similar systems, and he was always giving us feedback. Since we're theorists, we need the people who do the actual experiments to tell you that we're crazy and that would never work and we need to rethink our work because it makes no sense. So he was the voice of reason for us. All right, so the first thing is, what is quantum information science? So it's actually a really exciting field that keeps popping up with different names. So maybe quantum computing is something that you have heard about. It has been around for a few years, but then it didn't pan out to give the predictions as soon as people were expecting. So then we had that there was a name change, a rebranding. So instead of calling it a quantum computing, we now call it quantum information science. And the idea is as follows. If you have, let's say, a person, and this is a cartoon right here on the left, where we have Bob talking to Alice, trying to send a message. And if you look at the information science discussions, what they do is that they have this cartoon where Bob and Alice are trying to have a conversation, but then Eve is tapping into the phone line and being able to eavesdrop. In the case of quantum exchange of information, the transmission of information would happen in a way that you, if you're Bob or Alice, you both have a quantum key, and the encryption of the message is done in a way that when Bob sends it out, he sends it encrypted, Alice is going to have the encryption key, but if she tries to use the encryption key and the message is garbled, then they know that somebody tried to eavesdrop on them. So Eve was trying to get the information, but by this being a quantum system that she's trying to do, when she tries to measure it to grab the information when she was not allowed to have the key, then she messed up the whole information and nobody could hear it. So this makes it so that is, if somebody was able to drop into your communication, you would know right away that they were doing it. And you're secure that if you got the message, nobody was able to grab it before you. And also that the safety of the message is there because it cannot be unencrypted. Another aspect is that you would be able to process information faster, so at least that's the promise. So there's something that I'm going to talk to you about in a little bit, but for now, let's look at the following. And then this is the manipulation of spins. The electrons have a spin, so here they're saying that they're manipulating, and this was the cover in 2008 of the Science magazine that they had back then. So you can manipulate information, you can control it, you can do quantum processing so that you can do calculations way faster, and the transmission of information safely. So those are what quantum information promises to us. Now, if you have seen the news recently, actually not so recently because it has been happening for a while now, we have that this D-Wave qubit processor is available. And in fact, NASA and Google bought one. And the idea is that this machine is not a normal Intel CPU or anything like that. It's a complicated machine that uses the bizarre effects of the quantum world to give you the information, to do calculations for you, to sort something, things like that. So Google and NASA bought one in 2013, and they have been collaborating between the two in ways to learn how to use this quantum computer. So this was on the news. They're still working together. They have an updated machine, so it's not just the D-Wave 2 anymore. There's other ones that are getting more and more complex. And in fact, recently they had a claim that they were able to do a calculation that would take thousands of years for normal computers in the quantum computer. So they said that it is working. That's their claim. So how does it work? Well, before getting into that, let me tell you about two things. This is the most important physics behind it. How many of you are familiar with Schrodinger's cat? Let's see, how do I see participants? All right, so about two of you have heard of Schrodinger's cat. All right, so the idea of Schrodinger cats was put forward by Schrodinger here. So this is Schrodinger. Schrodinger is one of the fathers of quantum mechanics. His way of calculating is what you would learn if you took quantum mechanics. Is the wave function and is Schrodinger's equation, calculating the wave function of the system. So one of the things that a wave can do is that it allows for it to have solutions that are superpositions of two waves. And what happens here is that if you have the quantum mechanics, you have as a solution the wave function, you take that wave function and it's a probability wave function of things to happen. So in this case, this is the thinking experiment that Schrödinger came up with. He said, let's say that we put a cat and the cat is in a box. This cat is inside of a box, and inside of the box, there's a mechanism that is connected to a poison that would be released into the box if a nuclear atom decays. So what quantum mechanics tells us is that the nucleus, which is described with quantum mechanics, is in a superposition. If you don't measure it, the superposition stays there. It's in a superposition that is gonna decay or it hasn't decayed. Decay or no decay. That's that superposition that we have. There's a probability of it decaying after some time. And then that probability of decaying, that it has decayed, grows, and the probability that it hasn't decayed decreases. But it's a superposition of those two probabilities. The wave function of the system, of that nuclear system, is that probability. And quantum mechanics also tells us that it's not until we measure that event, did that event happen, yes or no? If it hasn't happened, then this probability of it hasn't happened wins, and it's now 100% that it hasn't happened because we measured. But if we haven't measured, then they're both probable. And then if we measured and it has already occurred, then this probability won out. But it's not until you measure the experiment. So what Schrödinger said is, let's put the cat in there, let's set up the system, and it's not until we open the box that we would know for sure that the cat is alive or dead. But while we haven't measured the system, the cat is in a superposition state of dead and alive. Does that make sense? So ask questions if it doesn't make sense, and I'll try to be clear, okay? So now, that's the idea that Schrödinger said, and to show that quantum mechanics was probably nonsense and we needed something better than quantum mechanics. But it turns out that this is completely true. What Schrödinger was saying, that a macroscopic system would be reacting like this and be in a superposition of alive and dead. I mean, nobody has done the experiment with a real alive cat, but they have done other experiments that show that this is true, that it's not until you do the measurement that things are in a superposition. So once you peak, you collapse it into one of the two possibilities, but before that is a linear superposition where it's both at the same time. So this is really weird, right? Raise your hand if you don't think it's weird. All right, so then that superposition and is the ability of a quantum state to exist in multiple possibilities, multiple states at the same time. And then the second thing, so you guys know this fellow right here, that's Albert Einstein. And this is called the EPR paradox. So Einstein, Podolsky, and Rosen said, quantum mechanics is wrong, and let me tell you why. And then they proposed the following experiment. So one of the things that we know from special relativity is that information cannot travel faster than the speed of light. We all agree with that, right? So if you have a system, take this blue ball right here in the center, that's the system, and it could be a molecule. Let's say it's a hydrogen molecule, or it could be whatever you want that could be separated into two. If it's a composite system, like a hydrogen molecule, you will have that it has a proton, it has two protons in it. And as a molecule, one of the protons is a spin up and the other one is a spin down. So that's if you had two electrons, there would also be a spin up and spin down. But basically, the two of them, when they get close enough to form a molecule, they would also show themselves to be one in a spin up and one in a spin down. So now here's the idea that Einstein and his buddies proposed. They said, let's say that we have that system and we all agree that one of them is going to spin up and one is going to be spin down. So now we separate them, One of us takes this system over here and I have it on this end. And then the other one takes the other system and have it on this other end. So quantum mechanics tells us that one particle is a spin up, the other particle is a spin down, but there's a 50-50 chance that this one is a spin up or this one is a spin up. So the property of a spin has to be measured for you to be sure which one it is, this one or this one that is a spin up. So at this point, they say, here, we know that one is up, one is down, and we don't know which one it is. So it's like a superposition of those two. And then we move them away from each other. And then let's say that one of you in one room measures this one. And once you measure, it's up. Then another person in another room far away even would say like, okay, I'm not measuring mine, but once the other person in the other room measure theirs and turns up, this one pops us down. Before that, they were in a superposition of up and down, both of them. But one of them got measured, then the other one pops the other way, instantaneously. So that's what the laws of quantum mechanics tells us, that if you take those two particles, taken far apart, the two are in a superposition, but they're also entangled because they were correlated, joined together at the beginning. And once you measure this one up, this one is down. So Einstein said, quantum mechanics is wrong because it allows for the transfer of information faster than the speed of light, because it's an instantaneous transfer of information. And after that, there has been several ways of doing this measurement, and they have all shown that this is actually what happens. So what Einstein proposed to say, this is wrong because it violates special relativity, that the speed of light is the fastest that information can travel from one place to another. The experiments have shown that yes, but this is also true. Due to entanglement, the two particles are linked together, and you would have that up and down done instantaneously. Does that make sense? Raise your hand if it makes sense so I can see who's following. All right. So one of the most important things is that these experiments have been done and they have shown that what Einstein proposed is actually how the universe is working right now. However, it's not completely true because when the experiment is done, there's always a loophole that somebody finds and said like, oh, there's a loophole here. Maybe Einstein was right and quantum mechanics is incomplete. So one of the proposals has been that quantum mechanics is incomplete and there's something hidden because these were not in a superposition, but actually this one was up and this one was down the whole way. And the information didn't get transferred from this one when I measured this one to be up, this one to go down. So that doesn't seem to be true though. That's what some proposals have been, and it doesn't seem like it's true. It's more like what I'm telling you, that there's a strong correlation between them. They were linked together at the beginning. They were in a superposition of up and down, and when you measure one, the other one collapses into the other one. And that's really weird, but that's how quantum world works. And another thing that I wanted to mention is that people think that Einstein or Schrödinger, because they're proposing these things, don't believe in quantum mechanics. It's not that they didn't believe in quantum mechanics, it's more like they wanted to challenge what was established as true. They didn't want to be they didn't want it to be like everybody believes this, like if it was something that came down from heaven, right? They actually wanted to challenge it and say like, look, this doesn't make sense. Is there something better? Well, it turns out that what they were proposing is actually exactly how the universe is working, and we actually are able to test these things, and it looks like this is how it works. So even though it makes no sense, this is how it works. And they haven't had to come up with a new theory that replaces quantum mechanics to describe these things, because this is exactly how it's been working. All right. So let me move forward. Superposition and entanglement are the two big principles here. And then if you were to look at the Onion, and I'm sure you all know the Onion, right? They had an article a couple of years ago that said that the scientists at the Haggard's PPL, that's the Pants Propulsion Lab, were bombarding khakis with high energy pleat particles. And then inside the article, it says that they placed the pants in a casual land setting and discovered them to be functional and comfortable. But against all logic, in subsequent tests, the pants perform equally well at a formal business luncheon. So they called this the Schrödinger pants duality. And they had this couple of pictures on there where they're showing how the pants behave well in both settings. So they had just developed the quantum slack. That's what the Onion said. So you guys know this is not true, but it's just supposed to be funny, right? Very few people would take it seriously. But if you look at The Economist, it actually doesn't, it does a way worse job of explaining you how this works, because at least in this setting, you're hearing at the Schrödinger duality and things like that that are true, and they're twisting it into a comedic way. But here they don't tell you anything. So you look at Economist. The Economist is a magazine that a lot of people read. And they had said, like, The Economist tells you what's a quantum computer. So in this particular setting, they were saying that a quantum computer could solve rapidly. And then they said, but in principle, challenges called NP-complete problems. And then they said, well, if you keep reading the article, it doesn't really tell you how. It just says that there's a strange fuzziness. And that's how it works, with a strange fuzziness. So yeah, if you're an engineer and you say that something works through a strange fuzziness, you're probably not gonna survive, right? So anyways, let's look at what they're saying. They're saying NP complete problems. So there's, everybody has problems, but when you have a problem mathematically, it can be solved, that you have different rankings of how hard it is to solve it. If you have a P problem, it's easy to solve if you're given enough time. So you raise the complexity of this P problem, and you just they're given more time and you can solve it. So for instance, if I ask you to multiply two numbers together, 3 times 3, you know, is 9 right away. If I give you a 3-digit by a 3-digit, two 3-digits numbers, and I ask you to multiply them together, you're just gonna take a couple of seconds longer, right? So the growth in complexity and the growth in time that it takes you to solve that problem, multiplication, makes this a polynomial time problem or a P problem. So now there's NP problems. An NP problem is one that the calculation grows exponentially complex if you increase the size of the, let's say, the number of digits in your problem for an NP problem. However, if you have the solution, there's a way to check that the solution is correct. So that's an NP. So it's a non-polynomial time problem. It's easy to check the solution, that you got the right solution, but it's hard to reach that solution. So let me give you an example of this. This number on the bottom is 2 to the 67 minus 1. So there's something called a Mersenne primes, and those Mersenne primes happen to have 2 to some value, some number, minus 1. So if you have this number minus 1, you get this number. And there's a question as to, people have been looking whether numbers, like for instance, if this is 2 to the 2, that gives you 4, right? Minus 1 gives you 3. And then the question would be, is 2 to the 2 minus 1 a prime number? And you already know that 3 is a prime. So that's correct. Then if you go to the next one, 2 to the 3 minus 1. What is that? 2 to the 3 is 2 times 2 times 2. You get 8. Minus 1 is 7. Is 7 a prime number? You know it's true. And then you continue going like that. And some of them are prime, some of them are not prime. But you don't know beforehand until you check all the numbers to see if it's a prime or not. So is this a prime number? Checking this by adding a digit here, you make it exponentially more complex. And checking this is actually a really easy solution, right? So now, is this a prime number? Yes or no? And you can do the factorization of this number. It takes a long time, but somebody did it. So there's a math teacher in the 1900s. He went to a conference and said on the factorization of Mersenne numbers. And so he shows up to the meeting. They give him 10 minutes to do a presentation. He goes up, he doesn't say anything. He just writes two numbers up on the board, this number, and then does the long multiplication. He multiplies it out. Frank Nelson in 1903, he multiplies these two numbers, and then he gets this bigger number here. And then he gets an standing ovation. Everybody starts clapping because they just realized that this guy, in less than 10 minutes, he proved that this number is not a prime because it can be factorized into two numbers, not one. So took him less than 10 minutes to show it, but this figuring out whether this was a prime or not, it took him about 30 years of his free time. So over 30 years, he had been spending his free time multiplying numbers together to see if he could get this number out. So that's an NP problem. Easy to check the solution. It just takes 10 minutes. But the calculation to figure out what was the solution took him decades. And there's an extra thing that is called NP complete. So this is an NP problem, non-polynomial solution problems. NP complete is a problem that you cannot check whether the solution is correct. You find a solution and you don't know if it's the right solution. So let me give you an example of an NP complete problem. What is the most efficient route that a mailman or the UPS delivery guy or whoever you want has to take to deliver this many packages, right? So you could define your efficiency. You could say we want one that doesn't spend as much gasoline. Okay, that's how you define efficiency. But then it's not until you try all the possible routes that you're gonna find the chore is more efficient or whatever type of route that you wanted. It's not till you try all of the possibilities that you know that if you guess at one, whether it would be the most efficient or not. So that's an NP complete problem. If you find the solution to an NP complete problem, you can map all the other NP complete problems into it and have the solution to a lot of very difficult optimization problems. So P problems, easy to solve. NP problems, easy to check the solutions. NP complete, you have no luck. It's extremely challenging. So Peter Shor, this is picture here from MIT. He's actually one of the experts in quantum computing, the architects of how it should work and all of that. He's one of them. And what he said is that a quantum computer, so it's not the economist talking anymore, this is Peter Shor. He said a quantum computer could dramatically speed up certain problems, such as breaking cryptographic codes. If you have an integer n, find its prime factors, and model quantum systems efficiently. So that's the things that it can do. This quantum computer, because it's quantum, would be able to model quantum systems. The thing that that was done over 30 years to figure out if an integer n had prime factors, a quantum computer would be able to give you that solution too. And this is really important for governments, right? A quantum computer, I mean, also for commerce, but the government would be really mad if people get a way to break cryptographic codes. Because for instance, when you're sending out your information, your credit card information or whatever it is through the internet, what they do is that they have 128 bits of encryption. So if you have that, a quantum computer could grab that problem and spit out the answer of what the encryption is, and you wouldn't have any safety in how your information is being sent. So that's the things that a quantum computer could do. So now let's talk a bit about bits. How many of you are familiar with bits? Raise your hand. All right, so if you have a bit, what you do is that you have a 0 or a 1. The computer processes these bits in a way like you send it the processor inside your computer, and there's millions of processors in it, right? What it does is that it sends it through gates. And the gates tell you how to do things with the bit. It can process the information. So for instance, one of the gates is called the NAT bit. So this NAT bit is gonna grab the 0 bit, run it through this NAT gate, and it's gonna turn it into 1. If you have a 1, run it through the same gate, and it's gonna turn it into a 0. So this is the NAT gate. There are other types of gates. For instance, this is the XOR gate, which is an exclusive OR, and it's kind of like the inequality function. So if you put 2 numbers here into this gate, those are your inputs, and your output is gonna be whether 0 and 0 are equal or not. So are 0 and 0 equal, or unequal, sorry, are 0 and 0 unequal, and the answer is 0 for false. Is 1 and 0 unequal? And the answer is true. Is 1 and 1 unequal? And the answer is 0 because it's false. And then if you join two numbers together, sorry, you bring in 2 numbers, you can add the 2 numbers with the exclusive OR and the inequality function. So this is how you would add 2 numbers. So for instance, A and B are added together, and you're gonna get 2 numbers out, S and C. If A and B are 0 and 0, both C and S are 0 and 0. If A and B, one of them is 1, and the other one is 0, it doesn't matter which one it is. As you can see here, A is 1 and B is 0, or A is 0 and 1 and B is 1. You would always get that S is 1 in both cases. But then if A and B are both 1, and in binary, if you add 1 to 1 and 1 is not 2, it's actually 10, then you get the answer to be C is 1 and S is 0, which converts into 10. So that's how you start adding digital numbers with transistors, basically. That's how your processor works. Christian, you have a question, or is that your hand from before?
Oh, that must be my hand from before.
Oh, okay, good. No questions, right?
I'm following pretty good.
All right, so now let's talk about how a qubit works. So qubits is a quantum bit. So you could have qubits be represented by particles. We could have the qubits be an electron spinning up or down. I like electrons, so let's go with electrons spinning up and down. But you could actually have that the particle could be an atom, right? And atoms also can have a spin up and down. And then the only thing that you have to have for a qubit is that it can be either 0 or 1, or a superposition of 0 and 1. So a bit is 0 or 1. A qubit could be 1 and 0 at the same time in different, maybe different, is more likely to be 1 or is more likely to be 0, but it can be both at the same time, and it's not until you do the measurement that it pops into 0 or to 1. So this is the most important thing. How does it work? So you have that the qubit can be in a superposition. So for instance, this qubit is a 1, the blue one. This red qubit is spinning the opposite way, is a 0. And in a superposition, it would look yellow. So you start with a quantum state that is a superposition. And in this case, let's say that we had 16 qubits together. The quantum computation would be the following. You have 16 qubits in one place. This is your quantum computer. You put them all into a superposition. And the way that you do this, it doesn't really matter, but you could do some magnetic fields, laser pulses, something to control them so that you put them together and they're in a superposition. Now, once you do that, what you do then is that you manipulate these states. And again, you put the manipulation, and it's usually the time evolution while under some control parameter. So in this case, is by shining a laser field. And you could be controlling this individually with a laser by pointing at them and making them do the operations that are achieved with the gates. So pumping a laser here might be a NOT gate, pumping a laser here might be a NOT gate, and so forth. Then you do this time evolution, and then you measure out the final state of the system. And you have to have a way to measure what is the final state, how do they look like. So this is how this would work in a processor. Let's say that we had a superposition that is alpha times 0, or alpha percent 0 and beta percent 1. Alpha plus beta would equal to 1. So it could be 1/2 and 1/2, or 1/3 and 2/3, and so forth. So in this case, alpha is up to here, and beta is up to here. And you run it through the NOT gate. You manipulate it in a way that you get the same as a NOT gate. So this alpha beta gets shifted to beta alpha. So now that means that this qubit is now this much 0 beta and alpha percent 1. So that's the NOT gate. The NOT gate flips it. If it was 1, it would flip it to 0, right? And if it's 0, it flips it to 1. But in this case, it's in the middle or somewhere in between the two. So if it was here, it flips it over here. And that's the transformation that you will get with the NOT gate. And you can manipulate the whole qubits in the superposition to do things like this and start getting additions or number or whatever you need. So now here's the cool thing. If you have 16 particles, you have a superposition that can represent 2 to the 16 numbers. So this quantum computer with just 16 qubits would be able to manipulate the whole world of 65,000 possibilities. Over 65,000 possibilities can be tested at the same time. So let's say that your problem was, how do I sort through 65,000 names? How do I sort if this name is inside this list of randomly put numbers of 65,000? The quantum computer, if it's programmed correctly, would be able to tell you the right one is this particular entry. And then searching through that entry would be hard, but then going through searching for the whole database might be hard. But if you go to that entry that it told you and you check, is this the name that I was looking for? It just takes you a millisecond to check, right? So it's really easy to check whether the answer was right. And if you didn't get it right, you just try it again until you get it right, which is probably 95% of the time the quantum computer will get it right. So that's the idea there. Or if you're multiplying numbers together like Frank Cole was doing, the quantum computer in the same amount, with the same effort that it takes to multiply two numbers together, actually would be able to multiply 65,000 combinations. That's the idea behind this. That's the power that it has. So you just have to figure out a clever algorithm that will give you what you want. And then once you measure, make sure that you're able to see if this is the correct answer. So that's how the quantum computer works. This is an example of it from research. This is about 10 years old, but it hasn't changed too much. You could have a system that is made out of silicon where you could put an electron on this end and another electron on this end. This L, R, and T are made out of gold. So you have a silicon wafer, you etch it with things so that you have this two positions for the dot. It's called the dots because that's where the electrons go and rest. It's an artificial kind of atom here and here. And then you have that the L, T, R, and this thing called QPC are gold leads, gold wires that are put on top. So what you can do is if you run a voltage to your gold wire, you're modifying what's here. All right, I see you, Jared. And then if you change L and R can be manipulated, or T, to figure out and move the electrons around and control it. So that would be your manipulation through sending voltages in the T, L, and R. And then the measurement is done because you're running current through here. So if you have running current through here, through this quantum point contact, you measure how much the current resistant is, the current moving through here has a resistance. You measure that resistance, and that resistance is influenced by whatever the state is over here and over here. So you can measure out what is the state of this system over here and over here by running current here and looking at the value of the current. So this is what you could do to create a 2-bit quantum computer. You prepare it, you put the 2 electrons together by raising the voltage in L, so reducing the dot over here by pumping the electron on this end. You separate it by reducing the voltage on L, and now you have the 2 electrons here. Look that over here, they were close together, so now they're entangled together. Over here, they're in a superposition. They evolve in time. Maybe you shine a laser on it so that you have some control, some gates acting on this one or this one. And then you bring them back together and you're able to measure what is the final state of the building, of the system. And that will give you a quantum computer. So here is that thing. I'm not gonna have time to go through the whole presentation, but the thing is that you have to do this before decoherence destroys your state. So this is where my work comes in too. So decoherence is the idea that electrons, so if you had a quantum system that is isolated, then things work marvelous, right? But if you have a system that is inside of a particular place, like in your room or in a room, the electrons have a memory time. So after 300 picoseconds, they forget what they were doing. So they have a tiny amount, you have a tiny window to do all this. After 300 picoseconds, half of the electrons have lost the memory of what they were doing. And that's when decoherence destroys the state. So you think that you have, in this case, that you were doing the calculation, but then decoherence kills what you were doing because the electrons forget that they were going spinning this way, and all of a sudden they just pop the other way without even being prompted to drop. So that's what decoherence does to the system, and it destroys what the information you had. And in a sense, what we want to do, so the qubits have an operation time of 100 picoseconds, but because it's interacting with the rest of the universe, it takes about 300 picoseconds to dephase them. So you will have to do calculations in 300 picoseconds, and each calculation takes you 100 picoseconds. So let me go to the end just to show you the picture at the end. Let me see. Here we go. So what we do is that we have the electrons on C. The charge can be equally on the left or on the right. So this is the system that I have. 2 quantum dots, they're pictured right here. And then what we do is that we have this perturbing one of them by kicking just one of them with a scanning probe. So then if you have the 2 electrons, you start them 0, both of them are together here. And then we have calculated what is the laser, or in this case, the kicking that you're gonna do with this scanning probe on one end of them. And we found that you could do in 33 picoseconds, you could do it so that you convert it from being equally on the left and on the right to just being on the left. And this is the time evolution that we did for that. So in 33 picoseconds, we just broke the record by being able to fit three manipulations instead of just one in 100 picoseconds. So that's the idea behind the research that I do. I could probably spend an hour talking about how to do it. But for your assignment for today, what I want you to do is to come up with the questions that you have on quantum information or something related to that, and then just write it out on your on the assignment page. Okay. Questions before we close? All right, so that's the main assignment for today. You have to just come up with a question on quantum information. Hopefully it's related to what you heard today, but if it's not, I'll be happy to answer it too. And you just type it into the assignment page that is going to be posted later today. All right, that's it for today.